So welcome everyone, this year's first TDS webinar. My name is Gabor Oros, and with Wim Michels, we have been guiding this series for a while. And today, it's my great pleasure to introduce Professor Rifat Sipahi. So Rifat and I have been knowing each other at least 20 years, something like that, right? So he did his PhD at the University of Connecticut, and after swing in France, he actually landed in Northeastern University in Boston, and he has been there since then. He's been very active in the field of time delay systems, both in terms of producing interesting and exciting papers, and also helping organize conferences, workshops, and so on. So without any further ado, Rifat, the floor is yours.
Thank you. Well, thank you, Wim and Gabor for inviting me, and thank you for the introduction, and thank you for everyone for sparing an hour, or maybe a little less, with me today to talk about time delay systems. And so I chose a topic to be a little bit in line with a particular direction I'll talk about some singularity problems that I ended up seeing over and over in the past maybe 15, 20 years in this line of research. And every time, maybe sometimes in a surprising way, these singularities appear in front of me, and then they end up actually giving a clue about a solution. And so I tried to kind of compile for you a couple of examples along with some theory. And I'll try to walk you through those. And two things I will need to apologize for upfront. I couldn't cite every single paper that came to my mind because it would be just impossible to fit everything into slides. So if any citation is missing, please ask me or email me and I'll complete. I didn't mean to exclude any relevant citations, although I added some citations for sure. Second of all, sometimes or often our results in manuscripts are in really clean and refined manner. So sometimes I copy pasted some content from published work, obviously with credit. And again, I apologize for doing that. I hope that doesn't look too inconvenient. All right, the presentation is really going to be focusing on time invariant systems, linear time invariant systems, and with constant delays. And I'll primarily look into asymptotic stability and gamma stability, which I'll try to define in a moment. Before we go ahead, obviously, maybe for a crowd that is really enthusiastic with time delays, there's not much need for a motivation why we study these types of problems, and they appear in numerous applications, and we know that for sure. And before we proceed, I'll tell you a story in a moment. So I thought I would share the slide with you first. I read this paper when I was in grad school, and one of the authors, Zaihua Hawang, is someone I actually end up meeting years later. And this is one of the papers that inspired me between the connections using algebra in the context of time delay systems. And especially his manipulation of some equations using polynomials using Sylvester resultant elimination technique was, to me, really exciting. So I'll get back to this discussion later in the slides. All right, let's continue. So the types of problems I will refer to today are in the state space form of this type, where A and BIs are matrices, and by n delays tau I are constant. And we have this general state space form, and we would like to maybe analyze its stability. So I'll be a little bit more formal when I say stability a little later on, but for now, let's think about an asymptotic stability in the sense we understand. And one question that arises is, if the matrices are given, A and BI, right, for which delay values will this system exhibit asymptotic stability? This is one of the main problems that bothered in the literature for over 60 years in various different forms: single delay, multiple delay, n by n, 2 by 2, 1 by 1, and many others. Now, what we know is sometimes it will happen that the system will be stable for an amount of delay, tau 1, in the single delay case, and then will be unstable for any delay larger than some critical value. In some cases, the system actually may exhibit more than one stable region or interval or pocket, we call, and this is something we know how to analyze. When we go to a two delay problem, and then we talk about the regions of stability in sort of intervals of stability, And again, there may be multiple regions of stability that are disconnected from each other and disconnected from the origin of the delay axis. And for those delay values, the system may be stable. In this case, the gray region is where the system is stable. And so this is a question that we are really interested in answering, and there are solutions to answering these questions in the literature with different levels of difficulties. The connection here is that, first of all, obviously we know this, maybe a little tutorial here, even if you have one single delay, in the case of A and B are matrices, this problem is quite difficult, because if you write it as an eigenvalue problem, where S is a Laplace variable, S appears on both sides of the equation. So there's no simple way to solve S out of this equation for a given delay tau. And or conversely, for a given tau, what S value satisfy this equation is not a simple task. And of course, if you go to multiple delays, this becomes much more difficult, because what delay values will work to make this equation to be equal to each other, and S appearing on both sides is going to be a really difficult problem to solve. This is a nonlinear eigenvalue problem. And remember that A and B are matrices. So when you expand this or you try to compute this, this is going to be a nightmare. And let's interpret this to what happens a little bit, just very graphically on the complex plane, as the S being the solution of the characteristic equation, right? When a delay is 0, everything is easy. We have finite number of poles. I'm only drawing the upper half of the complex plane for simplicity. But as we increase the delay, we know that we have infinitely many poles, and then those poles actually arrive from the left half complex plane from negative infinity, and they will eventually merge into the area of interest, and especially they will get closer to the imaginary axis as we increase delay values. So this complex plane is going to be populated with infinitely many eigenvalues or roots of the characteristic equation, and these poles will move along some trajectories, and there is a risk that they will cross the imaginary axis. And if that happens, then there is a risk for instability. And these crossings happen at some particular points on the imaginary axis, omega star, for a given delay tau star. And this point of crossing is really important because it signifies the transition point between a stable and unstable behavior of the system. And to summarize, and if you look at it a little bit more single or multiple delay or two delay problems, the link between complex plane, right, and the delay axis or delay plane, right, to stability, he really hinges upon the fact that there are some delay values for which a crossing happens, and these crossings are the separating points on the axis, whether it's one delay, two delay, or so many delays. And of course, this is a necessary condition for a system to be from stable to unstable. The reason being that if the system is already unstable, another crossing will just make it more unstable. So there may be other black dots in the stable, unstable regions, indicating that the system is actually gaining more and more unstable poles as the delay increases. But it's very important to find the crossings because they actually inform what stability, instability, decomposition will be in the parameter space of delays. This is more or less, in general, can be broken down into two problems, into two steps. Find all the delay values for which a crossing happens, which is not a simple task to do. And then once you find all those delays, use sensitivity analysis to identify which sides of the regions are stable and which sides are unstable. I don't want to oversimplify the approaches. There is hundreds of papers on this topic, and because it's easier said than done. But I'm not going to talk about these in super detail, but I want to just emphasize that this is not a very simple task to do, to find these stability regions. And that's why there's tons of papers on this topic. Now, going back to stability, a little bit maybe formally, at least we know that for this type of problems we are looking at, retarded class systems, stability holds if and only if all the poles of the system or eigenvalues of the state space system lie on the left half complex plane. So from that point of view, you can kind of associate these with ordinary differential equations, except that we have to deal with infinitely many poles. There is another definition which kind of is used to infer performance, is gamma stability. So not only you may be stable, but your poles may have certain distance to the real axis. And in that case, we will call that system a gamma stable system. And so in the middle picture, gamma is 0, and the right-hand side picture, gamma is positive, which is undesirable. So the performance analysis, which is usually in literature is associated with the rightmost poles, eigenvalues, adds more information about the system, because stability is important, but we also want to know how much gamma we have in the system. So that is actually a really important additional piece beyond stability. So that adds significantly more information about what you're able to do and what dynamic response you anticipate from the system, if you can at least practically approximate your system's behavior based on the rightmost pulse. And there are a number of really good computational tools available in the literature, and with no particular reason, we often use TraceTD and QPMR, but they're all capable in many different ways. I'll show you a lot of examples with TraceTD and QPMR in a moment. And whenever I fail to provide the full citation, I will provide another citation at the end. But I assume that everybody knows TraceTD, QPMR, BIF2, Lambert W, and Yalta. And I'll proceed with that understanding. Again, gamma stability will be additionally important beyond just stability. Let me just give you an example of what I'm trying to say here. So imagine that you have a first order plant, a simple first order transfer function, control with the PI controller, but in the feedback line, there is 1 second delay. I don't give you the specifics because they're not really important what numerics are, but at the end, what you can find a region that looks like a D shape inside which the system is stable. The PI gains inside this region will make the system stable. And the gray color that I computed with TraceTD indicates the gamma value. So how much gamma do we have in the system? And obviously these are negative gammas because the system is stable. And if you then go back and zoom in with sufficient resolution, if you compute this, you can find that gamma to be around minus 1.78. All right, so what does it mean? It means if I choose different PI gains, although they're all stabilizing, they give different results when you have a step response. And obviously we are interested in a response that is likeliness, less overshoot, less undershoot, sufficient settling time, etc. So different PI gains give you different results, and all of them work against delays. All of them are stable, but which one is better depends on what the gains are. So there is a bit of a motivation behind the value of gamma stability, and I'll talk about this in a moment in some other examples. Here's the first problem about singularity I want to talk about. So this is a problem that has been studied in the literature in so many ways. So imagine you have an input delay. This is a consensus problem. You have agents that are trying to reach a consensus. Alpha are constant gains, positive, and subject to some graph graph structure. Obviously, everything is connected properly. So, and in state space form, it looks like in this form. It is in this form, and it is significantly simpler than what we have seen in the previous slides in terms of state space format. Something really interesting happens if you compute the rightmost poles, right? And the poles in the beginning start somewhere around here, and they will follow these green arrows. They will go left first before they turn around, and they go to right and cross the imaginary axis. So as you increase the delay value, the poles go away from the real axis, while at the same time, some other poles arrive from the negative infinity. And then at some point they meet together, and then as like a big flood of poles, they turn back towards the imaginary axis and cross the imaginary axis and make the system unstable. For us, what was really interesting is why do these poles go left when we increase delay from 0 to 0.1, 0.2? Why don't they go over to the real imaginary axis directly? Why they go away from the real axis, imaginary axis? And we try to prove it. And so if you write the characteristic equation under some good conditions, A matrix A, you can decompose it if A is upper triangle. If you can triangleize the A as an upper triangle, we'll be able to write it and decompose the problem in this form. This is a manipulation that you may see a lot in the literature. And one interesting problem here is that this is obviously looks like a scalar problem on the right-hand side, but lambda can be complex numbers. So you can think that this is actually a quadratic problem and in the S square, if you want to create real coefficients. So what we can do is we can assume that, not assume that, we can say that the S actually has a real part sigma and an imaginary part j omega. And if you can plug in and consider that the lambda is a complex number in polar format, rho is positive, theta is the orientation angle. And then we have n number of locus along which these poles actually are formed, right? So we need to analyze this for all the subsystems. And then let's see what happens. Now, when we take this characteristic equation and rearrange it we can arrange it in real and imaginary part, and we can separate it, and then a little bit with a simple manipulation, we can create two functions. When a sigma curve, we call it omega curve. If these two hold at the same time, then you have a solution. And turns out that the omega curve, which we can write in this form, has a very interesting shape. The blue curve, as you increase the delay value, starts to distort, becomes like an egg on the right-hand side, so to speak, and has another curve that emerges from the negative infinity. And these two blue curves actually approach each other and they meet somewhere in the middle. And that kind of explains why the poles are actually going away from the imaginary axis, because this blue pole, right, potentially represents where a blue curve potentially represents where the poles are, if the sigma curve also holds at the same time. So we start investigating where this meeting point might be, and that required some partial derivatives to vanish. And if you and the equations actually end up easily manipulable, such that you can derive the condition for delay value for which the singularity will happen, meaning a meeting point will happen here between the two blue curves. And at that point, turns out that sigma curve is automatically satisfied. You can actually show that that actually has a 0-0 division here. So and all of this depends on the magnitude of the eigenvalue of A, nothing else. So if you know, and E is a natural logarithm base, and if you know the magnitude of the eigenvalue, you will find the delay value for which the pole will be the farthest from the imaginary axis if lambda is actually a real eigenvalue, because we are looking at the omega equals 0 line. So in other words, this is what happens. You have a lambda equal lambda A eigenvalue when delay is 0. As you increase the delay value, another pole starts arriving from negative infinity. And as you keep increasing delay value, they move towards each other. And then at some point, they will meet each other at that critical delay value, which we can calculate analytically. And moreover, this is for the real eigenvalues, real lambda A. If you have complex lambda A, we can also prove with some, again, singularities, that if your eigenvalue of lambda A starts below the 45 degrees line here in blue, it will always go left first before it goes right. If your eigenvalue starts above the 45 degrees line, then the eigenvalue goes directly to the imaginary axis and crosses it. So if you're designing a system of this type, and if you pay attention, the eigenvalues of A to be below the 45 degrees line, you will be able to actually secure a better potentially settling time from your system when your delay is not 0. So this is now. Let's go to the second problem in terms of singularities. One interesting problem is detecting the crossing frequency set, the exact bounds, upper and lower bounds. Let me give you a sense of what that means on a 2-delay problem, and I'll extend it to multiple delays. So imagine that you have a crossing at omega star for some special values of tau 1 and tau 2, right? Excluding the exceptions, if you perturb the crossing value, you'll find another delay value, tau 1 and tau 2, a different value, such that another crossing happens, right? There are special cases this won't happen, but in general, it will happen, all right? And if you just keep perturbing, there's going to be a point that there'll be no more crossings, and that is a crossing range, all right? So that's the big, large capital omega. The capital omega represents all possible locations through which a pole can cross the imaginary axis. And this is known to exist for retarded type systems, so nothing to question. There was going to be a finite upper bound, and it will obviously have a lower bound. And only in this range, the poles can escape through to the right-hand side, or they can come back to the left-hand side by a reverse action, reverse movement, right? But this is really important because only through these passages, right, the poles can go through left half, right half plane movement. And so it's important to know what's the range of these, set, upper bound and the lower bound, especially the upper bound. Of course, what may also happen is the lower bound can be 0. That's a possibility. And of course, the omega can have multiple disjoint sets. So sometimes poles will escape through these multiple disjoint sets as they move. They can maybe go from left to right from the upper sets, and then they can go back from right to left from the lower set. So these things may happen, that there may be disjoint sets. Now, the crossing frequency set has been a very important focus of calculation, because if you know what for crossing, what the omega is, you have a chance to find what tau is, and then you can study stability. And this problem has been extensively studied, and for a single delay problem, it is solved. For multiple delay problems, it was not solved to the best we know until we studied it. And again, in the general sense, I'll try to expand it to multiple delays, but let's look at the problem in 2 delays. How do we approach this? So before I do anything else, I have to show you a substitution that many of you know that I have been using for maybe 15, 20 years now. But I have to use this transformation to show you actually how this works, because that transformation is really a link to, in my opinion, to enable the solution. So this is I attribute to Recasius and this is a bilinear transformation. And many of you know this from maybe from other research areas. And but to the best we know, recasters use this in the context of time delay systems for the first time. Propose that a transformation on the right-hand side can be replaced, can replace the exponential functions in the characteristic equation. And propose that t is a real number and s equals j omega. So actually the actual transformation is written like this, right? So whenever you see an exponential with minus j tau omega, you can replace it with the right-hand side. And an easy way to convince ourselves is to plot these two functions on the complex plane. They both sit on the unit circle, and they both have a phase angle, and they have a map from A to A prime to A. If you know one point on one circle, you can find the other point in the other circle. And the phase angles must satisfy this relationship. As long as this relationship holds, this transformation is valid. And again, there are so many papers on this. So maybe for now, trust me, this actually is true. This holds, and you can do this substitution. And most of my work has been spent on, especially in PhD, on extending this to multiple delays. So now if you have an exponential function with tau 1, you have one transformation. Another exponential function tau 2, you have another transformation, and then their individual mappings. Then I guess, as you can see, it's still pretty complicated because you have to deal with different variables T1 and T2 instead of exponentials. But you can also appreciate that the right-hand side is algebraic, if I can manipulate it a little bit, and it's going to be a polynomial instead of dealing with complex transcendental functions with exponentials. Right. I still have to deal with some transcendental functions when I do inverse mapping, but again, there is no simple way around this anyway. So now, to the best we know, the exact range of omega for multiple delays has been studied for some time, and I'll show you how we approach this. So now let's take a look at a very simple problem. So I can walk you through the numerics a little bit. Sorry, it's going to be a lot of numbers, but it will be easy to follow. Imagine you have an oscillator open loop system, s squared plus 10, and you want to stabilize it with a proportion controller, but arrive at the delay of tau 1, and a derivative controller, KDS, but the signal arrives with tau 2. So this is a very weird PD controller. Proportional is delayed by tau 1, derivative action is delayed by tau 2, and you're trying to stabilize a harmonic oscillator with s squared plus 10 transfer function, 1 over s squared plus 10 transfer function. All right, let's just maybe do this recursive substitution. And because s equals j omega and t is real, these two cannot be 0. So you can expand this and eliminate the fractions. And you can organize it with some, let's say, a gain of 2 and 0.5 as an example. Right? You can organize this in this really nice form. In the nice form in the sense that there are no more exponentials. It is a multivariable polynomial. T1 and T2 range plus minus infinity. S is a Laplace variable. And now we are looking for an S equals j omega solution for this polynomial for a T1, T2 real. We want that omega to be as maximum as possible because we want to find the range of the omega set. It's not an easy problem because if you try to plot this, it's going to be a big mess. I'll show you what the plots look like first. Before we go forward, let's look at this paper. I'm pretty sure you all know what this paper actually does. If you actually open this paper, you will see that for the multiple delay case, in other words, imagine you have tau 1, tau 2, tau 3, tau 4, tau 5, tau 10. And if you write the recursive version, it will be T1, T2, T3, T4, up to T10. So you will have S to the 10, S to the 50, whatever, right? So you will have S multiplying a multivariable polynomials, same structure, but instead of T1, T2, you will have T3, T4, T5, T6, all of them. And that's the exact structure this paper actually shows to be an NP-hard problem when it comes to stability analysis. And so through the recursive substitution, we are not eliminating the fact that the problem is NP-hard. But for low-dimensional problems, the problem actually becomes tractable. And it's still not trivial to solve it. And I'll try to show you how we did this. All right, let's move on. Let's put S equals j omega and separate into real and imaginary parts. So here's what we want to do. Find a T1, T2 such that omega becomes a maximum and satisfies these two equations. What's the maximum omega that satisfies both of these equations for a T1, T2 real and T1, T2 in the range of plus minus infinity? All right, if you plot these one by one, it becomes a mess. There is no way, obviously, graphically to figure out what omega is going to make both of the equations satisfied, and find the maximum omega. And obviously, you can't plot plus, minus, and minus infinity range at the T1, T2 values. And that's not what we want to do anyway. All right, what do we want to do? What we want to do is we want to find, first of all, common solutions of these two functions. And for that, we can apply the Sylvester's matrix. Going back to the second slide, third slide, when I cited the paper of Zaihua and Sylvester's matrix, and I use this in many problems. And here it said the Sylvester's matrix can be constructed, and the roots of the determinant of this matrix, right, contain the roots of the common solutions, right? But not the other way around. Some of the roots of this determinant are not common solutions, but for sure all the common solutions are encapsulated in the G function. This is good news because I eliminated the T1 variable through the Sylvester's matrix. Now I actually projected the problem into a lower dimension, only omega and T2. T1 is out of the loop. The cost of having maybe additional superior erroneous maybe roots that I have to filter out later on and that don't satisfy both of them, but all the roots that satisfy both of them are actually inside the G function equals 0. That's good news. Let's plot the G for visualization. G looks like this, right? Unfortunately, I can't solve omega out of this equation explicitly because omega goes to power 5 and 7. Right? If it was omega squared, I could, but omega power 7, I can't analytically solve omega and then explicitly optimize this function and find these upper bounds, right? Where is this maximum omega happens, right? Can I find these points? Those are singularity points, right? And if I had the function omega, I would do d omega dt2, right? Try to optimize this, but I can't do that because I don't have an explicit solution of omega. But I know that I have the G in implicit form, and at the minimum, what I know is that for a singularity point to exist, right, the numerator has to be 0. Maybe the denominator has to be 0 too, but at least necessary condition is that I have to have dg dt2 to be 0. I need that to be 0, so I take a derivative from the G and obtain the derivative with respect to T2. And both of these functions now have to be 0. I can do another Sylvester's matrix. This time I'm going to eliminate T2 because I want to know omega only, right? I'm after the omega. I can eliminate T2, which is somewhat means that I eliminate all the effects of tau2, right? In some sense, right? And if you do a Sylvester's matrix of a function against its derivative, that's called the discriminant. And that's the famous discriminant we know that we use a lot, especially for quadratic polynomials. But this discriminant definition exists for higher order polynomials as well. All right, so what happens if I eliminate T2 between these two equations? Well, I will have another function that is only a function of omega. Some of its roots are erroneous. I will have to eliminate them. But for sure, all the relevant roots are in the solution that I'm looking for. Relevant roots meaning the singularity points, because that's how I set it up. I enforce it to give me the singularity points. And so now all I have to do is I have to check if any of these are feasible. I can go back and substitute the omega to the previous function, which is only a function of T2. If T2 is real, I go back up and substitute and find T1. I can go back up, substitute T1, T2, and omega, check if these two functions are satisfied. If they are, then that's a feasible solution. Now let's plot this for the sake of visualization. And all of these actually, these numbers that are analytic, we found them from analytical functions, right? They actually match up the curve and in its sensitive points and singularity points. And especially also the asymptotic catches those. And then if you go back and implement a separate algorithm and compute the omega numerically, you find, and so sorry, you can also verify that 372 corresponds to real T1, T2. Again, the bottom omega 2.58 also corresponds to T1, T2 real. So it means those are correct solutions. So omega should be at least between 2.58 and 372. You can do the same for other omega values, but I didn't do it. So you can actually identify that there are two disjoint sets of omega in this problem. And then you can then numerically verify that it's true. So this is the index number that I computed, all the omega solutions of this characters equation. And you can see that all the omega values from the numerical results match up with the analytical results. And indeed, we have two disjoint sets of omega through which the poles can escape left or right or left. Why is this important? Let me give you an example. This is important because if you know your omega range, then you can do some type of frequency sweeping in the exact range that you need to do, then compute to tau 1, tau 2, tau 3, tau 4, and you can find your stable or unstable regions. I'm not going to show you that because I'll show you something else. Next problem, I'm added a damping in this problem. Otherwise, it doesn't work, what I want to show you. I added a little damping in this problem, and I computed my second discriminant one more time. I'm speaking maybe 10 steps here, but same procedure. And now I have relaxed the controller gains. A very simple control gain design. What controller gains do I need to have to do something, right? I'm not setting them to be fixed, and KP, KD are fixed. There are 6 coefficients, C1 through C6. And these are polynomials in terms of KP and KD. I didn't put them in here. They're a little lengthy, but you can plot them without any problem. And these are now polynomials in terms of KP, KD. And let's say, and this is this second discriminant is going to be even function of omega. That's easy to show because roots are in complex conjugate form. And so omega square, let's just set that equal to t. And I want to show you something. And then I reduce the power to t6, right? And the leading coefficient is negative. That will be very important in a moment. Now, what I want to do is I want to do the following. I want to make sure that this polynomial has no positive roots. In other words, I want this system, my time delay system, to have no feasible omega set. There is no upper or lower bound. There's nothing. Omega doesn't exist. In other words, I want the system to not able to make its pulse cross the imaginary axis. And I want the omega crossing frequency set to be empty, to be an empty set. But for that, I want this polynomial to have no positive roots in T. There's a beautiful result from Descartes. I rephrased it for the sake of this presentation. And it's written more elegantly than I could write here. But it says that if all these, in this problem, the leading coefficient is negative. So if this consecutive coefficients, -4, C1, C2, C3, all agree in sign, then the polynomial has no positive real roots. In other words, if this is -4, and if C1 is a negative quantity, C2 is negative, C3 is negative, up to C6 is negative, then I'll guarantee that there are no omega square solutions to my crossing frequency set. And it means the poles can never touch the imaginary axis. Why is that good? Well, this is a sufficient condition, by the way. The sign sequence that I just explained you, it's sufficient, not necessarily sufficient, but it was sufficient to show some good results. So first of all, in this example, if you put Kp and Kd equals 0, you can verify that the C1 and C6 are all negative already. So it means the origin of the gain space, Kp equals Kd equals 0, all the coefficients are already negative. So obviously the origin is already delay independent stable. No surprise, because if you put Kp equals 0, Kd equals 0, the system without control is already stable. So it's delay independent stable when there's no control, right? Then you can plot C1 and C2, C1 through C6 on the plane, and you can show which region is going to be delay independent stable. And that's the kind of the promise that I was giving you. So in this case, I could plot C1 through C6 as a function of Kp, Kd. And you need to use implicit plot, but you can do it. And because I know that the origin is delay independent stable, and as long as I don't touch the boundaries and stay inside this region, I will be delay independent stable. Now, if you are wondering what happens for single delay systems, there are some really good results there, especially this one by Zichen, Kegingu, and Carl Netz. They have an explicit formula with a spectral radius test that can give you a delay independent stability condition. But when you go to multiple delay problems, things can become a little bit more complicated as we demonstrate. All right. Now, just to summarize, we said, well, we can't use graphics. We have to use some discriminants and resultants. And you can take this now to the next step. Although it gets more complicated, I must acknowledge if you have multiple delays, not just 2 separate delays, right? You can imagine that this becomes actually an architecture of sequential discriminants. It's in the literature, they call it iterative discriminants. So you go all the way down to multiple discriminants. At the very end, you have a function of omega only. It contains some omega resolutions that are not needed. You need to kind of clean them up and find the exact omega value. But you can do that because when you go one backwards, you can plug in your omega value and you have another one variable that you don't know, T5. Then T5 and omega, you go back and solve T4, T3. And so every time you're solving only one unknown at a time, eventually you need to verify that it satisfies, everything is satisfied as you constructed the polynomials. And this way you can actually identify the omega set, upper and lower bounds. What does it mean discriminant in the geometric sense? It's the discriminant in the geometric sense is the little games that we used to play with shadows when we were kids. Imagine that a light shines from infinity all the way to a complex shape object. 3D is easy, but obviously it can be ND. And then you have an image of the object on the wall as a shadow. In this example, all the critical points of the hand are projected onto a lower dimension on the wall, including those in the front, maybe here. Obviously, we don't see it, but right. And even the finger in the front with the discriminant, you'll be able to capture that. It will be actually in the calculation. So all of those are actually projected onto a lower dimension. Let's just give an example of what that means when we use a sphere, right? It's simple enough to show what we expect in terms of the shape of the shadow. So imagine I shine a light against the sphere. And what happens is that it's going to be a circle, right? We know it's going to be a circle when project it. And if you do a discriminant operation, you get a circle, right? So what it means is take the function f, take its derivative with respect to x, and then eliminate x. It means the light is coming from in the x direction. It shines onto the plane of yz, and the image is going to be on yz, and you get a circle. Now, if you want to project one more time, then you can project it onto, let's say, the y-axis. Now, if you shine the light along the, so let's project onto z-axis. So if you shine the light along the y-axis, all the image of the circle is gonna collapse onto the z-axis as a line, and it will have upper and lower bounds, right? And those lines are going to be what you will project to, and you can find that upper and lower bounds are plus and minus 1. In a nutshell, that's what we have done with time delay systems with the recursive substitution, allowing me to manipulate the equations using algebraic tools. All right, now let's go back to the Sylvester's matrix, because I was at a conference and Professor Stepan is on the call. He was also one of the organizers, along with Professor Zai-Hua Wang, and this was in Nanjing in 2016. And I had the pleasure to meet him there. And he gave me a book of his. He wrote about this topic, an excellent book on robustness and delay systems analysis in the context of what I've been also discussing, and delay independent stability and using algebraic tools. So please check it out. And he kindly signed it for me. So I still keep it today. Another conference I had been to was organized by Professor Sabine Mondier and Professor Ruben Garrido. And during the visit there in Mexico City, I met now my colleague, back then a PhD student, Adrian Ramirez. They were working on an interesting problem. They showed me some of the preliminary results. They said, well, we have a plan transfer function. We have a controller that has an inherent delay in it. So we intentionally put delays in the controller. We know the structure of the controller, but we don't know the gains, right? Is there a way we can manipulate the controller gains in such a way that we can place the rightmost poles where we want them to be? But we want to do it analytically. I said, wow, how can you do that? Tell me more. Ultimately, they end up publishing results, many papers on this. And here's an example that I borrowed, and with their permission, they kindly let me borrow this. And because I want to show you the connection of how singularities propagate through different problems. Here's a problem, a DC motor control problem. Y is the velocity of the motor, and U is the input. B, A, B, C are constant. C is a disturbance. I'm going to ignore that because I'm just going to look at stability. E is the error between reference and the velocity of the motor. And they are actually working on this type of controller, which is called IR controller, integral retarded controller, where Ki and KIR are design parameters for the controller gains. And H is an intentional delay. So we put that into the system on purpose. And I'll tell you why it's important to do it on purpose, right? That will be a little bit towards the end. But let's take a look what they are trying to do. Given the coefficients A, B, C, so I know that the plant properly, and you give me a sigma value or gamma value, right? I use sigma in this presentation to respect their choice of variables. So given a sigma value, right? What gains Ki, KIR you need to choose? What delay you need to choose such that the rightmost poles will be at sigma and all the other infinitely many poles obviously will be to the left of the sigma. And how can you do that analytically? Or obviously this is problem specific, but there are many other class of problems. These types of approaches actually end up working. You can numerically compute this using QPMR or trace TDE. And for a given Ki, you can plot the delay H that you intentionally inject against the other gain KIR. And you will find these stability islands in gray scaling indicating how good your sigma is, how large your sigma is. Obviously, you want to make your sigma as large as possible. I'm almost finished. Sorry, it takes a little bit longer than I expected. Right, in this numerical computation, we know that sigma is going to be about 38. All right. How can we do this analytically? Well, if you start with the characteristic equation and if you shift the characteristic equation with S equals S minus sigma, so that you look at the rightmost location placement on the shifted measure axis. And if you play with some partial derivatives, again, no surprise, and to maximize the sigma this time, not the omega, but sigma, you want it to be maximum, then they arrive at a proposition that says each of these sigma critical points in each of these islands on the top right, sigma 0, sigma 1, sigma 2, they can analytically characterize it. Moreover, sigma 0 corresponding to the solution of this tan x minus x, when x equals 0, turns out to be the best one that they can prove. Best value, 38. Sigma 1 will be less than that, maybe 20. Maybe sigma 2 will be 15, who knows? So if you actually substitute x0 equals 0, you can refine the result and find a formula, an explicit formula in terms of only the model parameters and the desired sigma or the sigma value that these parameters will prescribe, and that will correspond to the sigma 0 value that we have numerically found. Then this is a really perfect match between numerical results and the analytical results. And then if you go back and plug in the numerical values they used, you can compute the exact value of sigma 0, 38.25 something. And that's very powerful, obviously. So now we're talking about a type of PID controller gains that are analytically described that allow you to place the poles where you want them to be using algebraic tools to find this formula. Moreover, they prove that these poles, when you optimize the sigma 0, there will be triple roots on the real axis where this happens. And the system, so in other words, the rightmost poles are triple poles at the sigma location or minus sigma. And there is a proof that they can show that those poles will not only be on top of each other, they will also be the dominant ones. And moreover, they can now rewrite this as a design problem. So if you would like to have a sigma that you would like, so on the right-hand side this time, they can tell you what Ki to use as a function of model parameters A, B. They can tell you what H to use, and they can tell you what KIR to use. And very importantly, turns out that this pole placement gives you a sigma value significantly better than A over 2 that you can ever accomplish without the control. So it's not, it's better than A over 2 that you could do without the controller. So better than open loop. So that is the answer to that question. And there are a lot of follow-up papers on this. I'll show you one quick example, I'll finish. I would like to tell you, give you 3 more papers that I would, if you are interested in this topic, have a look. One of them is Wim's and Silviu's book in 2007. They printed an update recently. So in there, Wim actually envisioned that these triple or multiple roots will happen on the real axis when, in certain cases, when the rightmost roots are placed farther from the real axis. So there's a really beautiful connection there to what Wim envisioned 2 decades ago, roughly speaking, and to what we are discovering. But you can kind of see how these results are kind of like adding on to each other and then a little bit partially overlapping, but some kind of building on top of each other. Triple pole placement is not something that is attributed to one paper. Please check out the work of Thomas Vidal and Pavel Zitek and Jemer Weiser. And also take a look at some other developments on multiplicity-induced rightmost roads led by Busada, and Niculescu. So I'm just giving you one or two papers by different names. So if you want to track these, you can do that very easily. Now, how does this go to the multiple delays with multiple dimensions or large scale problems? Here's a consensus problem we studied with Adrian. On the left-hand side is a consensus problem where we use intentional multiple delays and for position and velocities, just positions. This is a proportional, this is a retarder controller, so it's a PR controller that actually works on a double integrator consensus problem. You can create this in a state space, and then you can decompose it into a characteristic equation of this form. And now you can actually study only the factors in the S square. And now how do you choose two row values and the H value to make each of these factors happy in terms of sigma value? And because you use independent controller gains and dependent delays, you can actually design each of these factors independently so the factors won't compete against each other. We were able to prove that, we were able to, first of all, leverage the dominance index, meaning not only have rightmost roots at sigma, but you want the neighbor roots to be far away, so you have enough spectral gap. This way, you can have a better approximation of your infinite dimensional system as based on the rightmost poles without too much interference of the secondary poles. So dominance index in this problem cannot be more than 4.8, meaning 4.8 times gap we can create between the rightmost poles and the nearest secondary poles. And in addition, we can subscribe where the poles are supposed to be. And also we can actually show that how the Laplacian eigenvalues should be distributed such that everything will work out. And you actually get the sigma value you want from your multidimensional consensus problem. Here's a time simulation where we demonstrate that. So we choose different gamma values and different for a fixed dominance index of 2.8-fold. And we can show this in these gray regions on the right-hand side, vertical column, in the column. We can actually show that the way we designed, when we compute the rightmost roots, it's exactly how we designed it. So here we used QPMR to compute the pole locations, and we can really show that the spectral gap is something we can achieve. At the same time, we can achieve the rightmost poles to be exactly where they should be with the gamma value. And obviously, as you manipulate these spectral gap and where the rightmost poles are, you can then manipulate how fast you can reach consensus, and you can push the states back to equilibrium. Lastly, one may wonder what additional advantages we gain if we have an intention delay versus maybe a PD controller. So PR controller is a counterpart of PD controller, except that in the PR controller, you have a smoothing effect. The noise is, by the nature of PR, is actually smoothed out. And simply because in the PR controller, the retarded part is somewhat a derivative approximator. And for that reason, if you actually look at the body diagrams, you will see that and when you do that, you actually are able to reduce the sensitivity of the system against noise. And that is one additional advantage of using these types of delay-based controllers. All right, with that, I'll finish. I hope I was able to show you some ideas about singularities and how they appeared in my life, and they keep appearing all the time. And again, there are obviously new problems that they appear as we go. And I think, to me, the exciting part is how we connect the delay systems to algebraic tools. That's one part. Singularities are fun or not fun to work with, but they seem to tell us some interesting results. So when you see a singularity, don't go away, just pursue it, because there may be a good answer there. And of course, multiple delay problems, you can extend them to multiple delays mathematically, theoretically, but there are some computation challenges. Maybe there are some results there, maybe some colleagues in numerical analysis can help us with. And of course, when you have intention delays, you may have also unintentional delays. So what happens if you have unintentional delays and you want to add an intention delay? How do you make the system to work are some other open problems we've been working on. Lots of acknowledgements. First of all, thank you for inviting me again, Gabor and Wim. Acknowledgements to my colleagues that I heavily mentioned in this talk. And of course, if I fail to cite properly, I cite one more time, trace TD and QPMR here. And I hope I didn't take too much time. Thank you so much.